The broadcast is now starting. All attendees are in listen-only mode.
Hey y'all, can you see and hear me? Go ahead and raise your hand if you can. Hello, Mateo. Alright, great. I'm gonna wait a second before I get started. But because I do have a couple of you that are, that this directly affects, rather, I should say. Specifically Hannah and Josiah. I've got some big news for you. I have accepted a new job, so I will no longer be teaching the 4 p.m. class. I will be teaching the last of your Raleigh lab sessions, and I will continue to be teaching the 6 p.m. Young Engineers of Today class. I will no longer be teaching the 4 p.m. class, though. So Josiah and Hannah, do you have any questions about what this means for you? Because you normally attend the 6 p.m., so it shouldn't mean too much to you. But either y'all any questions? Mateo, this doesn't really mean too much to you either, since I am teaching the 6 p.m. as still. Any questions? The question is, can we start soon and quickly? I'm hoping that somebody else will come on before I get started. I have 3 people here right now. We're not doing processing today. We're switching things up. So give me another minute and a half, and we'll get started on that. I just wanted to let the folks in Raleigh know what's going on. You're ecstatic? Alright, cool, because I hope you can see this is what we're going over today. You're excited to begin, I see. Oh, okay. Alright, like I said, give me another minute or so before I get started, and we'll start talking about gravitational waves, since we're not talking about processing today. About halfway through our class, I will let those who are not here yet know about what's going on with me and scheduling. So again, I'll still be teaching the Raleigh labs, but I will no longer be teaching the 4 p.m. webinar. So alright, so I'll go ahead and get started. We're going to start with not processing, but we will be talking about gravitational waves. So actually, crap. So today we're actually going to be talking about gravitational waves instead of processing like we were before. The discovery of gravitational waves is one of the biggest discoveries in science since, depends on your mindset, but I'd say it's the biggest since either the transistor development or the nuclear understanding of nuclear science. So I am going to send you a link to a video that will get you started on what we are talking about today. And I will show you as well. I understand if you can't hear it very well. Like I said, I do have the link copied into a chat. But we're going to watch this video first to fully understand the implications of everything that is going on in the scientific community today. So let's go ahead and get started. So I'm going to put this full screen.
What are gravitational waves? It all starts back in 1915.
Someone else coming in real quick. I'm going to send the link one more time in the chat. We're talking about gravitational waves and not processing today because it's one of the biggest scientific achievements in a very, very long time. So let's watch a video about it.
With Einstein, he hypothesized that all objects with
hear it?
mass would warp the fabric of space-time. If their mass is great enough, those distortions could cause other objects to fall into them. This is what we call gravity. Einstein also predicted that these distortions could travel across the universe, stretching and squeezing space and time as they move. And this is what we call gravitational waves. Later, researchers realized that if two particularly giant masses, like two black holes, are trapped in each other's gravitational field, they should start to spiral in towards each other, and so would the distortions they make to space-time. This would create gravitational waves which would travel away from the objects like ripples in a pond. But as these gravitational waves travel through space, they'd become more and more difficult to detect. In fact, Einstein thought scientists would never see them, but that hasn't stopped them from trying. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. This is a conceptually simple piece of kit that aims to measure the distortion in space-time caused by gravitational waves. LIGO works by splitting a laser beam and sending it in two directions. The beams travel precisely the same distance down long vacuum tubes. They're reflected off mirrors, and then they come back and recombine. The light waves of each laser beam are made to exactly line up so that they cancel each other out and nothing will reach the light detector at the end. But if a gravitational wave passes through, it will minutely distort space-time, changing the distance each laser beam has to travel. That will mean that the waves no longer line up, they won't cancel each other out, and the signal will be detected. The experiment is hypersensitive to disturbances, and so two identical LIGOs were built on opposite sides of the United States. Both will have to get the same reading at the same time for any signal to be considered valid. LIGO is designed to directly measure gravitational waves. This is different from another experiment based at the South Pole called BICEP-2, which made headlines back in 2014. BICEP-2 is also looking for gravitational waves, but not directly. Instead, it looks for the imprint gravitational waves would leave on the cosmic microwave background. That's the afterglow of the Big Bang. LIGO, on the other hand, is looking for much more recent gravitational waves, created only a few 100 million years ago, by something like the collision of two neutron stars or the merging of two black holes. It's been almost exactly a century since Einstein first predicted the existence of gravitational waves. And now, with LIGO, we may finally be able to tell if he was right.
So that's a very basic overview of what we'll be talking about today with the gravitational waves. So give me just one moment. I am having some issues with one of my students getting into the webinar. So I'm going to pause my screen for just a second and pause my recording. So almost a week ago, scientists detected gravitational waves for the first time ever. It's a big deal. These were predicted by Einstein with his theory of relativity back in 1915, but it's never been observed until now, almost 100 years later, just due to the lack of sensitive enough technology. So, 100 years until the technology advanced to Einstein's genius. He's a really smart man. So this is the first observation of the universe outside of the electromagnetic spectrum. So the electromagnetic spectrum is what you see below, and I'll tell you a little bit of how this works a little bit later. But that includes light, radio waves, X-rays, UV rays, microwaves, infrared radiation, and gamma rays. So the wavelengths of the waves I'm talking about vary dramatically. The smallest waves that are emitted are gamma radiation, which have a wavelength about the length of a nuclei of an atom, so super small. We get up to X-rays, where we get to atom size, ultraviolet, then visible light, which is just a little bit bigger than the size of a virus. Visible light includes all the colors that you see here, and by here I mean in your room or wherever you're sitting. Then we get bigger to infrared, then to microwaves, then to radio waves, which are the size of like a football field. So this is the first time we've observed the universe outside of these electromagnetic waves. That's a really big deal, y'all. Like, the future of astronomy is completely changed. We are going to look at the universe a lot different than we did before. So let's talk a little bit about the facts of what's happening. Or specifically the facts of what happened 1.3 billion years ago. Because it does matter today, surprisingly. So these waves that we experienced, or LIGO experienced rather, occurred due to black holes in a binary black hole system. So binary meaning two black holes together, orbiting each other. So these holes were orbiting each other and eventually collided 1.3 billion, with a B, years ago. That's a really long time. That's like incomprehensibly long. That's about the time that bacteria started being formed on Earth. That's when this event happened, and we're just now getting the gravitational waves from it. So consider that. This actually was the first time that binary black holes ever were confirmed to exist. These are the largest black holes ever discovered, which I'll talk about later, and their collision released an enormous amount of energy. So if for some reason the Milky Way were to explode entirely at once, this is how much energy was released. Or if you prefer to think of it this way, if there were 66 billion, with a B, as in boy, 66 billion suns exploding at one time, this is how much energy was released. There's so much energy released that, oh goodness, it's not even possible to comprehend. There's a ton of energy. So this is a really big deal that we finally discovered these, which I'll explain later. So these black holes, like I said, were bigger than any other that we've found before. Each of the black holes was between 29 and 36 times the mass of the sun. So I don't know specifically how big the sun was, or how big the sun is, mass-wise. So let's just make a wild guess saying, I don't know, maybe 500 billion pounds or something. This is 29 to 36 times that. It's enormous. That's so much mass. Again, incomprehensible. But all of this mass was squeezed into a black hole, which has about 150 kilometers of a diameter. So that's the difference, or distance between Greensboro and Charlotte, or outskirts of Winston to Raleigh. This is a really, really small area in the grand scheme of the universe. So hugely massive black holes, but very tiny. These guys were spinning around at about half the speed of light, so incredibly quickly, and they fully merged together soon after their orbits reached about 210 kilometers of each other. So that's between Asheville to Charlotte. So again, back up, what I'm talking about is some of the facts about these black holes. Talking about how it sorta-ish proves relativity. It observes the electromagnetic spectrum, or it observes the universe outside of it. Huge black holes, and that's about all I've gone over so far. Or massive black holes, not huge black holes. They're very tiny black holes, actually. And the merger between these two black holes releases the energy of 3 solar masses. So if y'all remember E equals mc squared, E stands for energy, m equals mass. So 3 solar masses of energy. So that's 3 times the mass, and then times the speed of light squared. Basically, it's just a huge amount of energy, y'all. Like, mind-blowing amount of energy that these release. And that's why 1.3 billion light years away this happened. But let's talk a little bit more about how that happened. So let's talk about Newton and his idea of gravity. So y'all are probably vaguely familiar with Sir Isaac Newton. He's the guy that made physics. He did a lot of calculus stuff. Very smart man, but he was limited by the technology of his time. He said that gravity is a force felt between any two objects regardless of your size. So, let's take you and your best friend. You might not be together right now, you might be, but you and your best friend are always going to have a gravitational attraction towards each other. Gravitational, I'm saying. The closer that you two get, and let's just say the more you weigh, the higher this gravitational attraction will be. And that's just not you and your friend. That's you and the chair you're sitting on. That's you and the International Space Station. That's you and the moon. Every object that has mass, so almost every object that we know to exist, is attracted together by gravity. So he had a very good baseline knowledge of what we're looking for here. His knowledge basically accounted for the movements of celestial bodies, so the sun and the Earth and the moon, among others. His idea of gravity, or his law of gravity, or gravitational constant, I suppose, still is used for approximations in physics classes today, only when extreme precision is not required. Now, obviously, we're not trying to sit here talking about black holes and use this idea of gravity, but it worked back then when we had no idea what was going on. And we still don't really know what's going on. Anyways, Newton could not describe why these ideas worked or what gravity was. He said that gravity must be caused by an agent acting constantly according to certain laws. But whether this agent be material or immaterial, he's left to the consideration of his readers. So he doesn't know what's going on, but he knows that gravity is indeed a thing. It is indeed what makes the whole universe work. So let's talk about Einstein. He came about maybe, 300 years later, and he had a couple of ideas about gravity himself. He had two theories about what we call relativity, and I'll tell you about relativity in just a second. They're called special and general theories of relativity. I'm going to be talking mostly about general, but to let you know what special is first, special relativity basically says that the laws of physics do not change depending on the observer's frame of reference. So what that means is if you're on Earth, or if you're on a spaceship that's flying 1,000,000 miles an hour, most things are going to stay the same in terms of the laws of physics. Like the speed of light. No matter how quick you're going, the speed of light is going to stay the same. But some things might look a little bit different depending on your reference frame. So right now you're sitting in a chair. It seems like you're pretty still, right? But if you are on a spaceship, maybe, you can see that the Earth is spinning so quickly. You can see that the Earth is rotating about the sun so quickly. So special relativity is basically just saying, alright, the laws of physics are the same, regardless of if you're flying super fast or if you're seemingly stationary on a planet. No matter what's going on, the laws of physics are going to be the same. So, the gravitational wave discovery specifically, which is what happened about a week ago, proves a prediction about the second theory, which is the theory of general relativity. So what this says is gravity is a result of a mass's influence on the space around it. Massive objects cause a distortion in space and time. So massive being very, very heavy, basically. Very heavily, objects that have a lot of gravity, basically. They cause a distortion in space-time. This theory of general relativity predicted the existence of gravitational waves. So these are waves that'll stretch and squeeze space when sudden changes in mass occur, such as two black holes becoming one black hole. a lot of energy is released, a lot of mass is released, and therefore the overall mass changes. These waves do radiate outwards from the source, just like a stone thrown in a pond. And these waves move at the speed of light. So when I said earlier that we're looking at something that happened 1.3 billion years ago, the only reason that we can observe it is because it's just now hitting us. This stuff happened 1.3 billion years ago at a place that is 1.3 billion light years away. How do you know this, you ask? Computer models. Einstein's equations were incredibly accurate, and we are able to model certain situations based on the mass of an object, the distance of an object. There's a lot of stuff that we can simulate in a computer model, but the reason this is big is that this is not a computer model that we've noticed. This is something real that confirms a computer model. So let me go on some. So when I talk about space-time, I want you to visualize it as if you're standing in the middle of a trampoline. I hope y'all have been in trampolines before, right? You know, jump on them. If you stand in the middle of a trampoline, your weight is going to make the trampoline push down where you're standing, so in the very middle. So if you weigh more, the trampoline is going to be pushed down more. If you don't weigh as much, it'll still be pushed down, but not quite as much. So if you look at the trampoline, you'll notice that very near you, the slope of the trampoline, so just like a mountain slope, near you it will be a lot higher than it is at the edges of the trampoline. Which means that if you were to drop a marble near the edge of the trampoline, it'll roll towards the center slowly. But if you drop a marble very close to you, standing on this trampoline, it'll go towards the center a lot more quickly. So that's what I'm trying to say here. Stuff with a lot of gravity is going to attract stuff a lot quicker than stuff without a lot of gravity. Or, if you'd like to put it this way, light from the sun takes about 8 minutes to reach Earth. It's just based on the speed of light. The distance between the sun and the Earth makes it so that it's about 8 minutes for light from the sun to reach us. Now, it's been known for a while that if the sun were to disappear very suddenly, we would have about 8 minutes before the sun's light would disappear. But based on Einstein's models, he said that we would also have about 8 minutes of the sun's full gravity before Earth realizes, hey, we're not under the sun's gravity anymore. And once that happens, the Earth would just kind of fly off into space, and we would have a very bad time and probably die. Anyways, so what he's saying is that both light and gravity propagate at the same speed, but we haven't been able to prove gravity's propagation until now. We've had a good idea. They were indirectly proven, meaning that we didn't have direct evidence of these waves, but we had indirect evidence back in 1974, back when scientists were observing the orbital speed of a binary neutron star system, so two neutron stars rotating about each other. But what's funny is that the increase of their orbital speeds was predicted by Einstein's theory of general relativity, but it still wasn't direct evidence. It took us that long to figure all that out. So think positive, not so deadly. I'm sorry, I don't think we're going to fare very well without a sun. Unless we can figure out a self-sustaining reaction like a star is, I'm not thinking very positive. So before I go on, like I said, I mentioned earlier to a couple folks, for after today, I will no longer be teaching the 4 p.m. class. I got a new job. and it makes it so I cannot work the 4 p.m. class. I will be working the 6 p.m. classes starting next Wednesday, but next Monday I will not be working, not be doing the webinar. Mr. DeToy will be doing the webinar, and he's great. He's really intelligent, especially in terms of coding. But starting next Wednesday, I will only be doing the 6 p.m., and I will still be doing the Raleigh Labs. So I got a couple questions here. One about the heating of the Earth. My new job, I'm going to be working basically to take complicated programming stuff and make it easily understandable for those with minimal programming knowledge. Does that sound familiar to anybody here? Because learning here has definitely helped a lot. Yes, I mean just like you. I mean that y'all helped me be able to take complicated stuff and make it easy enough for non-technical people to understand. So I do mean like you, but just know that you all have helped me immensely in gaining this skill. So, what do you mean that your dad's gonna need that? Mateo. So, your question, Josiah, was underground heaters could help out. It will help out, but it's not going to save us ultimately if we're careening into the cosmos. He's not good at coding? Oh, okay, I see what you mean now. And I'm not the best at coding, it's just one of those things that I'm going to be learning. But that's going to be my new job. Like I said, I will be available through email, and I'm going to be here at all the 6 p.m. labs. This just means that if you're continually coming to the 6 p.m. the 6 p.m. webinar, I'm going to try to keep everything on the same page as Mr. DeToy. I'm going to do my best, but I do recommend attending the same class that you would attend normally. So if you normally go to 4, I'd stay at 4. If you normally go to 6, stay at the 6. And it's applied to the Earth's core because it's hot. Yeah, but the Earth's core, I guess it's finite, I guess it's not. But anyways, so while I have you all captive, I do want to say that tomorrow at, I think it's 5 p.m., Charlotte Thursday Labs are happening in Charlotte. And similarly, on Saturday at 10 a.m., the Saturday Labs will be happening in Charlotte. Raleigh Labs will be happening not this coming Saturday, but the 27th. So I will be your teacher there too. So let's talk about some more stuff that relativity entails. Yeah, you are a prisoner. I had a captive audience there, right? Right, give me 1 second. So let's talk about time dilation. That's something that that basically happens with black holes. I don't know if any of y'all have seen the movie Interstellar before, but it's very accurate when it discusses time dilation. Interstellar is one of my favorite movies, and I definitely had to watch it the night after all this stuff happened because now it's officially confirmed, basically. But anyways, time dilation is differences in how observers sense how time elapses. You don't even know what that is? What, time dilation or the movie Interstellar? Regardless, you're going to learn about time dilation. Oh, the movie? Oh, it's a wonderful movie. Very scientifically accurate, but I don't know what it's rated. So you might not be able to watch it quite yet. But I recommend it when you get old enough to watch it. But what time dilation means is that clocks that are far away from a gravitational source, you don't have to watch it. No. I'm just recommending it if you're interested in this stuff. But clocks far away from a gravitational source will experience time passing more quickly than clocks close to the same source. So what I mean by this, you can actually experience this on Earth, is that if you synchronize two clocks at sea level, so you're by the beach, you're hanging out, you have these two atomic clocks, you make sure they're at the same time, and you keep one at sea level, and you take one up to a very high elevation, like Boulder, Colorado, which is at least a mile up. If you give it maybe a week or two, you'll notice that ever so slightly, the clock at Boulder, Colorado will be ahead of the clock at sea level. Yeah, take it on top of a mountain. That's all you gotta do. It's saying that objects that are farther away from a gravitational source, just like a clock at sea level is closer to the center of the Earth than a clock on a mountain, the clocks farther away from the gravitational source will run faster. So time goes faster at higher levels. Farther away from gravity, faster time. So again, if you've seen Interstellar, they go down to a planet that's really close to a black hole. They lose like 21 years of their lives. Or I guess everybody else loses 21 years while they're down there. Anyways, let's talk about this in a little bit more sensical way. So you and your best friend, you're hanging out on this planet called Planet Far. This planet's very far away from a black hole, but you're an astronaut, and you want to go to a planet called Planet Near, which is very close to this black hole. While you're on Planet Near, time's flowing as usual. So you're chilling, you're doing your thing, just like you are right now. While your friend is back on their home planet, Planet Far, time is also flowing just as usual. But a lot more time is passing for this faraway planet than it is for the planet near the black hole. So if you leave this near to the black hole planet and return to the far away from the black hole planet, your friend is probably going to be a lot older than you are, even if you still look the same age as when you left. So basically what I'm saying is the immense gravity of black holes causes time to flow differently relative to the observer's position. So when I say relativity again, relativity means relative to whatever. Relative to an outside observer, maybe. Relative to, like I said, whatever. So, Sam, Planet Far, Planet Near, creative. I know, I'm a very creative person. What can I say? I made this whole PowerPoint, so. What I'm saying is time's going to flow faster if you're far away from places of high gravity. So, I'm going to talk about the formation of black holes now. But I'm going to talk about supernovas and neutron stars and pulsars before I do that. So black holes are parts of space-time that have such a high mass that not even light can escape. Black holes always start with an exploding star. Always. Except for the ones that started at the beginning of the universe, but those don't count. Nowadays, black holes start with a star exploding called a supernova. So supernovas happen, or supernovae happen when large stars... You started confused. Yeah. It's kind of hard to understand just the whole time dilation thing. I had to watch Interstellar a couple times to understand it. But supernova are caused when black holes have spent all their fuel for nuclear fusion. Nuclear fusion being the opposite of fission, which I talked about in the submarines. But fusion is when they force atoms together and it causes a lot of energy. Or creates energy, rather. When this happens, the star is going to explode, for the most part, if it's big enough. And if it's big enough, it's going to become a black hole. Small stars will not necessarily explode. They will become either white dwarfs or red giants. The sun itself is going to be a red giant when it dies. And mid-sized stars, like maybe 5 or so times the mass of the sun, will become a neutron star. And I'll talk about neutron stars in a second. What you see here is actually the remnants of a supernova colorized. It was called Cassiopeia A. So this is kind of what happens when supernova are still figuring out what they want to do with their past life. So neutron stars. So question is, what do you think would happen if the sun explodes? The sun is never going to explode. It's too small. When the sun runs out of fuel, it's going to become a red giant, and red giants expand in size. So yeah. Well, I guess I'm not sure. I guess something like a spaceship could explode the sun. Or the Death Star or something, but for now, nothing is going to explode the sun. The sun is going to do it to itself. And if the sun does die, it's going to become a red giant. It's going to become a whole lot bigger. It's going to encompass the Earth, and we're all going to die. Anyway, so let's talk about neutron stars. Neutron stars are the remnants of supernova. They are made mostly of neutrons. So, an atom has protons, positively charged, electrons, negatively charged, and neutrons, which are neutrally charged, meaning that they have no charge. Neutrons, being neutrally charged, do not undergo fusion. So they're basically dead. They are very dense. They're about the mass of the sun usually, but they have a very tiny diameter, so 14 miles, so not very far, a lot of mass shoved into a really small area. So some neutron stars are dense enough to collapse into black holes. Some of them. You might melt like chocolate in an oven. Maybe, I don't want to think about that because it's really depressing. Anyways, some neutron stars are stable enough to stay neutron stars. And some of these neutron stars that are stable rotate very quickly and release what we call pulsars. So pulsars are just neutron stars that rotate super quickly, and they're highly magnetic. The question is, what if the sun suddenly explodes? I have no idea. I have no idea what would happen. It wouldn't be good. We'd all die, no matter what. But that's all I can tell you. That's very dark. Oh my goodness. Okay. Anyways, pulsars are usually smaller than neutron stars. Melting suddenly. We'd eventually just sublime and become like gases and stuff. We wouldn't feel anything if we suddenly were to experience the sun becoming a red giant. We would all just die immediately, no pain. Probably be a good way to die. Anyways, pulsars are smaller than neutron stars, even though they have the same mass, which means that big mass, small stars means more dense. They emit pulses that can be observed within the electromagnetic spectrum, usually in the form of radio waves. And these pulses do not normally act along the axis of rotation of the pulsars. So imagine this rotation axis was a pencil, and you're rotating it by spinning the eraser on one hand and the lead on the other hand. That's how a pulsar would rotate. But the magnetic field of the pulsar is not necessarily along this axis. So it might spit out beams, this way and this way instead of going up and down on the axis. Don't worry about specifics on what that means. So we talked about supernova, which might cause a black hole, neutron stars, which might cause a black hole. One of the options of what could happen with a neutron star, but the other option is going to be a black hole. So black holes, again, are large enough to become supernova or neutron stars, or 5 times the mass of the sun. So when the fusion in the star's core stops, which again normally would cause a supernova, this means that all the elements left in the core are iron. So that's the biggest element that you can find in the core of a dying star, iron. Why? Not sure. But what happens basically is the lack of the pressure that's caused by the fusion. So stars are always undergoing fusion. This fusion has, a certain pressure to it. When this pressure disappears, the star starts imploding. as more and more mass is imploded towards the collapse or center of the collapsed star, it increases the escape velocity, which is the velocity required for an object to escape the gravity of this object. Eventually, this escape velocity is so high that not even light can escape. And that's what a black hole is. Gravity that's so intense that the escape velocity is higher than the light's escape velocity. So that's what a black hole is. So before I talk about how we detected this stuff, I'm going to talk about gravitational lensing, which is a way that we used to observe black holes. We can never see them, but we can observe them based on, scientific facts. We looked at black holes this way. We also looked at really heavy objects this way. But basically what would happen if, say, there is a galaxy behind a black hole, the black hole would bend the light around it so that we can see the galaxy just based on the different paths the lights went. So if we have, say, an object that is in the very center of this galaxy here, so maybe about right here where the things on my mouse are, it's going to bend light so we see many different images of this galaxy. So the sun could probably do it. If we were maybe 4 or 5 light years away and looking at the sun, we could probably see our Earth via gravitational lensing. But what happens is, say a big object is right here, light's going to bend around it in many different areas, so we can see many different images of it. There's only one image ultimately, or only one galaxy, but we can see several different images. The lens is caused by gravity and not just a clever use of optics. So it's not like how your glasses work by focusing a whole bunch of different light into one focal point, but it's a similar concept caused by gravity, similar to how that works. And what you see here is actually one of the first lensed galaxies that we observed. This is called Einstein's cross. We have a big galaxy here, and behind this galaxy, there's a quasar. And this is the quasar that we're seeing here, actually. So let's talk about how we detect these guys. So the people that detected the gravitational waves were called LIGO, which stands for Laser Interferometer Gravitational Wave Observatory. And long story short, they take laser beams and ram them into each other after bouncing them off mirrors. It's a lot cooler than it sounds, and I'll tell you how it works in a second here. LIGO has the most sensitive instruments of any gravitational wave observatories. They can detect deflections of light within the order of half an atom. Why can it not be Lego? What do you mean? Be Lego? Oh, because Lego is trademarked. I gotcha. But what this means, a deflection of light in this situation on the order of half an atom is real small, right? What this means, if you scale it up, is it's like detecting a change, maybe in position, of half the width of a human hair over the distance between Earth and Alpha Centauri, which is our closest star. It's about 4 light years away. So this instrument could say, oh, the tiniest movement happened over 4 light years. That's the equivalent of it in understandable terms. Super duper sensitive, like crazy sensitive. Like I read that they had to do their calculations and testing all at night because a truck several miles away would mess up their readings. But anyways, despite these instruments being very sensitive, they can still only detect enormous gravitational events. Sort of like 2 black holes hitting each other. A really big, enormous event. So here's the science they used here. Oop, wrong way. Light can be represented as a wave. So a wave, just like a wave in the ocean, just like that. So at LIGO, what they do is smash laser beams together, and their ultimate goal is to eliminate light. And I'll show you how they do this in a second. But the way they do it is they use destructive interference, which takes two different waves and combines them to make nothing. So we take one up, down wave, we take one down, up wave, add them together, we get nothing. That's what we're looking for, or that's what we normally have. Complete destructive interference, nothing crazy happens there. If something happens to bend this light, not all the light waves would destruct, and some laser light would be detected by their instruments. That's called constructive interference. So if something happens, just like gravity, which can indeed deflect light, these waves are going to get a little bit off and make it so some light does come through. So like I said, some light is bent by gravity, and that's what LIGO found. So let me go a little bit of background here. LIGO had two different observatories. They began their experimentation on September 1st, 2015, so not very long ago. 13 days after they set these instruments up, a gravitational anomaly was discovered, first at LIGO, Louisiana, which is pretty far south in the U.S., and milliseconds later, the same thing was found at LIGO in Washington State. So within milliseconds, they detected the same thing. This is because the speed of light determines how fast gravitational waves propagate, and they discovered that the difference in times that these things happened correspond with the speed of light. And these events really, really don't happen that often. Like, we think the universe is infinite and crazy stuff happens all the time, but the fact that we discovered an event like this not even 13 days after a big anomaly like this happened, that's big. That's really lucky. Like, we really rolled the dice and got lucky here, y'all. I'm sure these scientists were just losing their minds about their luck. So basically what this means is the origin of the anomaly comes from the southern skies. So we first saw it happen in Louisiana and then Washington State. We cannot triangulate this signal any further because triangulation means that we need 3 points. We only had 2 for this, just based on funding. But we have a general idea of where the event happened. And how they knew this was okay was that the waveform of the gravitational anomaly, I'll show you in a second what that means, corresponds with what scientific computer models predict for a black hole fusion. So again, science knows that using the mass of these black holes and the distance and how long ago it happened and all sorts of stuff like that, they figured all that out. And it took 5 months before they announced any discovery because they wanted to peer review it, which, if you all remember, is one of the big portions of the scientific method. You got to peer review everything to make sure that your data is able to be replicated, else it seems like you faked it and you're a liar. So let me show you what the waveform meant. It's kind of hard to see, and I apologize for that, but right here, the red, or the sort of red, is Washington's waveform, and the blue is Louisiana's waveform. So Louisiana saw this stuff first. And notice that when they overlapped the data, that their signals were very close together. They basically received the same signal at both of these places, just at different times. So after they discovered this, all sorts of people went over their data and were probably pretty mean about it, but ultimately it worked out for them because their data was guaranteed to be valid, and this discovery was proven. So let's talk about what happens here. Before I do this, I'm going to show you what exactly the LIGO detectors look like. They have two arms that extend 2.5 kilometers, which is about a mile from either side. So this is LIGO, Louisiana, and this is LIGO in Washington State here, so notice the arms. What happens here is a laser is fired. Boop, 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 laser light. And the beam splitter splits the light in half, basically. So half the light's going to go this way, half the light's going to go this way. The light normally would just bounce off the mirror of both sides, arrive back at the beam splitter at the same time, and go into the light detector. And usually when this happens, with nothing crazy, we're looking at nothing. We're going to see nothing happen. If nothing is detected, nothing's going to happen. But what happened here is after we fired this laser, we detected this gravitational anomaly, meaning that the gravity waves were able to deflect the movement of this light ever so slightly, again, half an atom, on both of these arms. So, light's bent on both these arms, would bounce back off the mirror, maybe light's bent some more, who knows. But what happens when all of this light comes into the beam splitter is that it doesn't completely undergo destructive interference. It doesn't completely just disappear. We're looking at some light that does come through the beam splitter, which shouldn't happen normally. It only happens when something big enough to deflect light happens, hence the gravitational waves. So, through this way, that's how we discovered that these waves are true. So, y'all are probably wondering, why did I just talk about this for an hour? This stuff is not that interesting. This is a really important experiment, like I said, probably the biggest in at least 50, 60 something years. Many firsts happen in this experiment. So it's the first binary black hole observation. They are the largest black holes we've ever detected so far. But the biggest implication of this is how our observation of the universe changes. So we still have the old methods of looking at the universe, so using the electromagnetic spectrum for radio waves and all the other crazy kinds of waves. But now we can actually observe the dark universe, which is stuff that wouldn't show up in terms of the electromagnetic spectrum. So far, we're literally just looking at gravity waves. This is the only way we have to observe the universe outside of that. So when technology in this field improves, we will be able to measure the how big the gravitational waves were of the Big Bang, or whatever was the origin of the universe. And measuring these gravitational waves helps us create a more accurate map of our position in the universe. So that said, that was all I had to go over today, so if you have to go, you're more than welcome to go.